So hi everyone. So now that we have an example for iterative, the reweighted least square. So at first we fit the model with the GLM function in R. Then after that we try the iterative reweighted least square method. And first we use just one iteration. Then after that we do multiple iterations to converge, to make the parameters converge. Then after that we discuss the variance of the estimate beta. Okay, so we use the faraway dataset, faraway library, and the dataset, the BLISS. So BLISS is insect mortality due to insecticide. So this is basically the binomial data, but this is the summarized. So for each the concentration of insecticide, we have the data for the number of the deaths and the number of the survival. So the the 2 insects are dead and the 28 are alive if the concentration is 0. But the concentration is higher, then the death is 27 and alive is 3. So it's much higher rate of death. And actually this data, the death plus alive, the sample size is always 30. Okay, so GLM function that we fit this data on this, the concentration and the binomial regression, and the default is logistic regression and the data BLISS. Then estimate for beta naught and the beta 1 hat is here. And the standard errors are here. So negative 2.32 and 1.16 are estimates, and the standard errors are 0.42 and 0.18 respectively. So now that we want to do this with the logistic regression. So the link function is the log of mu over 1 minus mu, so that is eta. And if we differentiate with respect to mu, then that becomes 1 over the mu times 1 minus mu. Variance, as you know, if the expected value, expected probability of success is mu, then variance of the observation is the mu times 1 minus mu over n. You can see that this function is maximized at mu is 1/2. So the probability, 50% probability is most uncertain situation. So variance is highest. So as we see usual, the mu and the v of mu is equal to 1/2. It's most uncertain. Mu is equal to 0 or 1, no variability. And W is calculated as this. So n times mu times 1 minus mu. And this is from the formula. So we don't really need to interpret, but actually the more variability, then if we have observation, basically the weight is higher. Yeah, because if we have the success probability 1% or 99%, even if we have many observations, probably information doesn't increase much. So that is one interpretation, that the weight is higher when mu is closer to 1/2. Okay, so the weighted least square only once, not iterated. At first we define y. Y is proportion. Mu is just the initial value, so just we use y as the initial value. So these are the sample proportions, and we define eta. So logit function is just this function, and z is the adjusted version of response. So we change the scale of y into the scale of eta, so that becomes this. Then we define weight. Weight comes from here. Then we fit the model, z on the concentration, z on x. Then weight is w. Then we get these estimators. And you can see even we just fit once. So these estimates are pretty close to the previous result. Previously, negative 2.32 and 1.16 but now the negative 2.30 and 1.15. So almost close. The standard errors are totally off. This was the 0.1. This was the 0.42 and this was 0.18. So it's totally off, but this is because the methods are different and this is inaccurate. So we estimate it later. Then next we repeat this procedure. So we use the fitted value of the previous model in the previous page. Then we repeat this again and again. So we redefine the parameter eta. Then we redefine mu, and then we redefine z and w. Then we fit it again. Then the next estimates are here. So this actually the approaches to our GLM functions output. And we try once more, then almost the same, but slightly different parameter. But after that, parameter becomes the same always. So it has already converged. So negative 2.32 and 1.16 are exactly the same as our estimates from GLM function. But still, the standard errors are totally off. So the estimates are accurate, but the standard error we have to calculate again. And remember that the standard error of beta, maybe to be exact, the variance estimate for beta hat is equal to x transposed the W x inverse times phi. But the phi actually in this case equal to 1. Normal case, that was the sigma square, but this is 0. Yeah, this is 1 this time. So x transposed y. So x is just the model matrix. The first column is intercept, and the second column is the concentration. And the weight matrix is here. Weight matrix is obtained by the formula in the previous page. So this times n times mu times 1 minus mu. So remember that the third column, maybe the third observation, we have actually the sample proportion of 0.5. So its weight becomes highest. It has most information compared to other observations. And the first one and fifth one, that we have the small or large proportion. The first one is small, last one is large, so we have smaller weight. And actually the first one is 2 over 30 and the last one 27 over 30. So it's not really symmetric at 0.5, but this is estimate. So estimated mu hat we use. And this is a linear model. So if the center is 2, 0 and 4 should be symmetric. So that's why we have the same weights. Okay, so using this x and w, that we can calculate this quantity x transposed wx whole quantity inverse. Then we get this. Then we get square root. Then we get the standard error of the beta naught hat and the standard error of beta 1 hat. And this should be exactly or almost the same as our estimate from the GLM function.